We're about to pull back the curtain on a really scary problem in computer science, the thundering herd. It's this phenomenon that's kind of governed by invisible physics, and it's capable of making these huge, complex systems fail in the blink of an eye.
I mean, just think about your digital life for a sec. Every single thing you do, every click, every tap, every search, it's all built on this sort of silent promise.
A promise that when you ask for something, the system will actually respond, right? We just take it completely for granted. It feels as reliable as flipping a light switch.
But what happens when that promise gets broken? For everyone, all at the same time. What happens when millions of people try to flip that switch at the exact same moment? Especially after it's been off for a while. Well, that's when the promise shatters, and you get a digital stampede. And listen, this isn't just some abstract theory. Matt Boyle over at Encore.dev shared this fantastic horror story. His team launches a big new feature, and in their excitement, they send a notification to everyone on the waitlist at the same time. You can guess what happened next. They unleashed an absolute torrent of traffic that just brought everything crashing down. They basically created their own thundering herd by accident.
And yeah, that's pretty much the textbook definition. It's this vicious cycle, you know? A service goes down, all the clients start trying to reconnect, and the second it comes back up, it's immediately obliterated by all that pent-up demand. It's kind of crazy when you think about it. All those well-intentioned retries, they combine to create a denial-of-service attack that you basically launch against yourself. Okay, so to figure out how to stop this, we first have to understand the basic physics of how systems handle requests. And it all boils down to something we're all familiar with, waiting in line, or, as we call it, a queue.
So how in the world do you measure a digital traffic jam? Is there a formula for that? Well, it turns out there's a surprisingly simple and really powerful law that governs pretty much any system where things have to wait their turn.
It's called Little's Law, and it's just this: L equals lambda W. So, the average number of items in a queue, let's call that L for length, is equal to the rate at which new items arrive, that's lambda, times the average time they spend waiting, which is W. L equals lambda W. I know, it seems almost too simple, right? But this little formula is so important for understanding how systems behave under pressure.
All right, let's make this real. Forget servers and requests for a minute. Just picture a coffee shop. Little's Law is just saying that the length of the line is determined by two things: how fast customers are walking in the door, multiplied by how long each one has to wait to get their drink. See? It's totally intuitive when you think about it that way.
And we can even use this to make some quick predictions. Imagine you walk into a Starbucks. You see 15 people in line. Okay, L is 15. You watch the barista, and it looks like they're getting through about 2 people a minute. That's your lambda. So you can just flip the formula around to figure out your wait time, W. It's just L divided by lambda, so 15 divided by 2. Yep, you're going to be waiting about 7.5 minutes. This simple law really does govern the flow of any stable system.
Okay, so what happens when thousands of these customers are all trying to access the same piece of data at the same time? Well, databases have to manage that queue, and they pretty much do it using one of two core philosophies: pessimism or optimism. Pessimistic control is, well, pessimistic. It's cautious. It assumes two people are going to try to grab the same thing at the same time, so it locks the data first before doing anything. It's safer, for sure, but all that locking and unlocking creates overhead and slows things way down. Now, optimistic control is the total opposite. It assumes conflicts are super rare. It just lets everyone read the data freely and only checks for any problems right at the very end. It's blazing fast if there are no conflicts, but it's a huge gamble.
And this graph shows you exactly where that gamble blows up. Look on the left. With zero conflicts, the optimistic approach, that's OCC, it scales beautifully. But now look at the chart on the right. This is the abort ratio. Basically, how often an operation just fails. With just one conflicting request, 80% of operations fail. At 10 conflicts, it's over 98%. The system is just spinning its wheels, doing nothing useful. This is the optimistic gamble failing, and failing spectacularly. So here's the takeaway, right? Pessimism is just too slow for modern needs, but pure optimism is way too fragile. It just falls apart. We need something smarter, something that can give us the best of both worlds. And this is where a really clever hybrid approach called Mostly Optimistic Concurrency Control, or MOCC, comes into play. Now, this diagram looks a little intense, but the core idea is actually pretty simple. Be optimistic most of the time, but be smart enough to apply those pessimistic locks only when and where they're absolutely needed.
And the key innovation here is this idea of temperature statistics. What Mock does is it keeps track of which pieces of data are hot, the ones that are causing a ton of conflicts and failed transactions. For all the cool, uncontested data, it stays purely optimistic and super fast. But for those hot records, it proactively slaps on a pessimistic lock, which stops the system from wasting time on transactions that were just going to fail anyway.
And the results? They're pretty stunning. Take a look at the top graph. That's throughput, basically how fast it is. Now look at the bottom graph. That's the abort rate. See how the other methods kind of force you to pick one or the other? You get high speed, you get high failures. But now, follow that blue line for MVCC. It hits the highest throughput while keeping the abort rate way, way down. It actually solves the dilemma. You get the speed and the safety.
So we've seen the problem and a really powerful solution for the database itself. But how can we prevent that stampede from even happening in the first place? Let's talk about some practical things you can actually do.
One of the most effective strategies out there is called rate limiting, and a classic way to do it is with the leaky bucket algorithm. Just imagine you're pouring requests into a bucket that has a small hole in the bottom. No matter how fast you pour water in, it only drains out at a constant, steady rate. If you pour way too fast, the bucket just overflows, and those extra requests are rejected. It's a brilliant way to smooth out those crazy bursts of traffic and protect your services from getting totally overwhelmed. And the leaky bucket is just one tool in what should be a whole prevention kit. You really need a multi-layer defense. So you've got rate limiting to cap requests. When clients do have to retry, make them use exponential backoff, but with jitter. That word jitter is so important. It just adds a tiny, random amount of time to each retry. Without it, all your clients would wait the same amount of time and then retry in perfect, synchronized unison, creating another stampede. Jitter breaks that sync. Then, of course, you have caching to absorb retraffic and circuit breakers, which act like a fuse in your house. They trip automatically during a surge to stop a small problem from turning into a total system meltdown.
So the thundering herd is this powerful reminder that our entire digital world is built on a foundation of these invisible rules and really delicate balances. We've seen how a simple thing like Little's Law governs queues, and how a clever mix of optimism and pessimism can build much more resilient systems. It just makes you wonder, right? What other invisible rules are we all relying on? And what happens when the next one breaks?